Let's talk about the effects of the intermolecular forces in terms of the energetics of the different processes that are happening. You'll remember back to the chapter on thermochemistry, we talked about the change in enthalpy and all those kinds of things, the heat of particular processes. We're going to sort of revisit that, except in terms of the phase changes that we've just been discussing, like condensation and vaporization, those sorts of things. So how much energy is involved in these processes in general, and can we calculate it? Of course, yes we can, and we will. Remember, the higher energy molecules are going to be lost from the liquid when they evaporate, and so that's going to leave the lower kinetic energy molecules behind. You can think of it then as drawing out the energetic particles, and in order for it to draw out the energetic particles, it's going to be an endothermic process. So vaporization is an endothermic process. That means delta H is positive. Endothermic, remember, endothermic means it makes my hand cold if the process happened in my hand. That means that vaporization has to absorb energy. The molecules have to absorb energy to vaporize, to get into the vapor phase. And actually, you're quite familiar with this because that's how sweating works to cool the body down. You get liquid on the surface of your skin, a cool breeze comes by, the molecules of sweat on your skin, the water and whatnot that's there, absorb energy from your hot body and allow those molecules to turn into the vapor phase. And so it produces a cooling effect on you. Your skin feels cooler because that energy was stolen by the water as it evaporated. So vaporization is endothermic. Write that one down, don't forget. That means the opposite of vaporization, which is condensation, must be an exothermic process. Now that one's a little bit harder to keep in track of. It means in order to condense, it's got to let heat out. And so it does that by letting heat out to whatever available environment or surroundings there are. So you bring the cold can of Coke out, and those warm water molecules can let out the extra energy into the cold can and condense onto the side. That's an exothermic process. That means delta H is negative, just to remind you there. So vaporization requires an input of energy. It has to absorb energy to overcome all of the attractions between the molecules to escape from the liquid phase into the vapor phase. So here we have some thermochemical data here. We've got delta H of vaporization or vaporization. Delta H vap usually is how we'll just say it. And so at the boiling point or at 25 degrees C, and that tells us how much heat change is necessary to allow the process of vaporization to happen. We call that the heat of vaporization. So here we have water, and water, notice, requires 40.7 kilojoules per mole at its boiling point in order to evaporate or vaporize. And notice it's nearly the same for rubbing alcohol there. Notice acetone requires 29 and diethyl ether requires 26.5. This is the amount of energy necessary for the liquid to vaporize. Now, while it's vaporizing, it's absorbing the energy from the surroundings in order to do this physical change, this physical process. So that delta H vap, or the enthalpy of vaporization, gives us information about the physical process. Remember, it's endothermic, and so it's absorbing energy from the surroundings. Therefore, delta H should be a positive value, as we see it is. And that also means if you were to set up the equation that the opposite process, condensation, would have the opposite sign. So depending on how you want to set them up, there's how they relate. So calculate the mass of water that can be vaporized with 155 kilojoules of heat at 100 degrees C. Now, that means we're going to have to know what the delta H of vaporization is of water. Where are we going to get that information? We're going to look it up, or it's going to be given to us. I don't expect you to memorize the delta H of vaporization for different compounds when you can easily look it up, especially given how many compounds there are out there. So we want to find how much mass, or what mass of water can be vaporized, how many grams of H2O, in essence, can turn into the vapor phase if you supply 155 kilojoules of heat and the liquid is at 100 degrees C, so it's right at the boiling point. Okay, so you warmed it up to the boiling point. Now you're going to supply this extra amount of energy, and that extra amount of energy is not going to go to increase the temperature of the liquid, which is something we'll talk about later on in this chapter. It's all going to go to turning the water from the liquid phase into the vapor phase. So we know how many kilojoules we have. We want to relate that to how many moles of water, and then we can convert moles to grams. The reason we have a relationship between the kilojoules and the moles is because when you look it up in the back of the book or in the table, the previous table, table 11.7, the bottom of page 501, you'll remember the number is 40.7 kilojoules for every mole of water. So I have this relationship, 1 mole of H2O equals 40.7 kilojoules. And then I can go to my periodic table and remember 1 mole of water is 18.02 grams of water. So I just make the necessary conversions. 155 kilojoules is what I was given, so that's what I'm starting with. And it's 40.7 kilojoules to every 1 mole. So that tells me how many moles if I stopped there, but I want to find grams, so I'll take the next step and convert to grams. That means 68.6 grams of water can be converted into the vapor phase, into steam from the liquid phase, if I supplied 155 kilojoules of energy. Now often I'm going to be supplying that on my stovetop, but sometimes in different ways. Alright, let's try another one. Calculate the amount of heat needed to vaporize 90 grams of C3H7OH at its boiling point. The delta H of vaporization is 39.9 kilojoules per mole. So here I have kilojoules per mole. And I want to find the amount of heat needed. So I'm going to start with the mass, convert mass to moles, relate moles to kilojoules through the delta H of vaporization, or delta H vap. Okay? So here we have propanol, that's 3 carbon atoms, and this propanol is going to be converted it's being vaporized, excuse me, and I'm going to find the amount of heat necessary to do that to 90 grams of the liquid itself. So my conversion factor is 39.9 kilojoules per mole. Remember, this is rubbing alcohol, propanol, and I can convert the number of grams to moles easily using the periodic table. So I'm doing the same kind of process except sort of in reverse compared to the last time. I start with 90 grams, I relate that to moles. Why do I have to go to moles? Because I only know how the amount of heat relates to moles. So I got to get this number into moles so that I can relate moles to kilojoules. If I had a way to relate kilojoules directly to grams, I wouldn't need to do this conversion. I could skip it. Okay, notice I have to supply 59.8 kilojoules of heat in order for 90 grams of propanol to vaporize when it's already warmed up to its boiling point. All right, let's talk a little bit more about this dynamic equilibrium process that I mentioned earlier. Remember, in a closed container, the rate of evaporation and condensation is going to be nearly equal. And so the amount of liquid is ultimately not going to change because every molecule that escapes into the vapor phase, there's another molecule that loses energy and condenses into the liquid phase. So they're always kind of replacing each other, going up and down, unless the container is left open. But ultimately, in the dynamic equilibrium process, there's ultimately no gain or loss of the vapor or the liquid. It establishes some amount of vapor above the liquid that stays essentially constant, giving it the vapor pressure. Remember, we talked about that in previous chapters. Okay, so we have this dynamic equilibrium process. We call it dynamic because you constantly have new molecules going into the vapor phase and new molecules coming back down into the liquid phase. It's not the same ones everywhere the whole time. So it's a dynamic equilibrium. And we call it equilibrium because it's the same vapor pressure and the same level of liquid that are there at all times. And they don't necessarily change by equal amounts, but they are always changing. And the ones that are condensing are equal to the ones that are evaporating. So here we have a liquid in an Erlenmeyer flask, and it's stoppered. And that means if there are no molecules in the vapor phase, some will go into the vapor phase. They'll get enough energy to escape the intermolecular forces that they feel and get into the vapor phase. But it's like it's like the space above the liquid can only hold so much vapor in it before some of those molecules that are in the vapor phase have to condense back down into the liquid. Okay, and eventually an equilibrium is established where some are being condensed and some are being evaporated. That's the dynamic equilibrium, and that's what gives rise to the vapor pressure above the liquid. So this pressure above the liquid we talked about when we were discussing partial pressures in the gas chapter. You remember doing some problems about collecting gases over liquids. We had to subtract the vapor pressure from the water itself that was in there. Perhaps you remember that. This vapor pressure is created naturally on its own by this process of evaporation, and it relates back to the intermolecular forces and how much energy the liquid has in general. The weaker the intermolecular forces, the higher the vapor pressure. Okay? Strong intermolecular forces means a lower vapor pressure, because a strong intermolecular force means those molecules really want to hold together so much they're not going to escape into the vapor phase very easily at all. Okay, so weaker attractive forces means weaker intermolecular forces means higher vapor pressure. It means those molecules can escape into the vapor phase a lot easier. They don't stick together as much. So when this dynamic equilibrium is created in general, the volume ultimately is not changing. But if you were to change it, how would that affect the dynamic equilibrium? So imagine if the volume of the chamber was increased. All of a sudden, you gave the vapor more room. And that means a new equilibrium would have to be established. And that means there would be a decrease in the vapor pressure inside the chamber, to which more molecules could vaporize or evaporate to fill up that extra space that you added. So you would have more molecules in general in that new space that you created to establish a new dynamic equilibrium process where you ultimately have molecules going into the vapor and back into the liquid. Okay, it only means the rate of both of those processes is equal when you have this dynamic equilibrium. So after some new period of time, eventually the new equilibrium would be established and a new vapor pressure would be present. Okay, equilibrium would be reestablished at this point. The vapor pressure would be the same as it was before you made the change to the volume. So looking at that in graphic terms, you can see here we've got, this is propane it looks like, and you've got an equilibrium established between the vapor and the liquid, and now you've made more space, so you're going to need more molecules in the vapor phase to establish a new equilibrium. And if you had less space, you would need less molecules in that space. But each of these three situations, after they've been allowed to reach the dynamic equilibrium, have the same vapor pressure. Okay, a greater volume means you need more molecules in there banging around, creating pressure. To reach the same pressure that you would if there was less space, you would only need a few molecules banging around to have the same pressure. So they have the same pressure, same vapor pressure in each one, but a different number of molecules in the vapor phase, and each of them all have a dynamic equilibrium established between the liquid and the vapor phases. So ultimately, it's a dynamic process that's going on here. And in this dynamic equilibrium, the system, the liquid and vapor, is going to respond to any changing conditions that you give it. So if you change the conditions, the system is going to shift to relieve the stress on the system, is how we're going to kind of describe it. So it's either going to shift to having more molecules in vapor or less molecules in the vapor, such that ultimately it can maintain its dynamic equilibrium. Okay? It's going to shift such that it reduces the stress on the system or relieves the effects of that change. So how does vapor pressure and temperature work? Remember, a higher temperature means greater kinetic energy, means more molecules are escaping into the vapor phase. If that's true, then a higher temperature means an increase in vapor pressure. That one's not hard to sort out if you can stop and think through all of those connections there. A small change in temperature could make a big change in vapor pressure because it all depends upon the intermolecular force. So just a small temperature change in water may not be that big of a deal, but a small temperature change in acetone may make a huge difference to the vapor pressure because it all relates to the intermolecular forces. So here's sort of a graph of all these different types of substances. And notice as we increase the temperature, how the vapor pressure responds. Increasing temperature is an increasing vapor pressure. That's the trend we see for sure. But notice how an increasing temperature in some of these compounds leads to an increase in vapor pressure much quicker than in others. And the difference ultimately is because of the intermolecular forces experienced. I drew a green line here at 760 millimeters of mercury so you can see where atmospheric pressure is at. And that means at atmospheric pressure, we expect to have a vapor pressure equal to the atmospheric pressure when these liquids have reached their normal boiling point. So what's the normal boiling point of water? You're going to immediately tell me 100 Celsius. And that means the temperature is 100 when the vapor pressure has reached 360. A substance only boils when the vapor pressure reaches the external pressure. Okay, so when does that happen? For water, that happens at 100 degrees. But if you change the pressure, you're going to change the boiling point. Okay? So if you take that same sample of water up onto Mount Everest, it's going to boil at a different temperature because it has a different atmospheric pressure pushing down on the surface of the liquid. When the vapor pressure equals the pressure, the external pressure, the atmospheric pressure perhaps, then the liquid will boil. Interesting piece of information there. Notice the boiling point for ethanol at 500 millimeters of mercury is 61.8, but the normal boiling point is when it's reached atmospheric pressure, which happens to be, what is that, about 77 degrees Celsius. Which of the following is the most volatile? Or which of the following can evaporate the easiest is sort of what we're asking. So in order to figure that out, we can use the chart, or we can try to figure out how much intermolecular forces exist between all of these things to make a comparison. Since we have the chart, there's no need for us to make a comparison. We can immediately tell that ether is the most volatile. Notice ether is the one here at the very far side, which can easily create a higher vapor pressure with the smaller temperature change. Therefore, it's the most volatile. Therefore, it has the least amount of intermolecular forces. So which of the following has the strongest intermolecular forces? Strongest intermolecular forces would mean that it has the highest change in temperature required to produce the vapor pressure needed to match the atmospheric pressure. So, titanium tetrachloride, or as sometimes is said, Tickel 4 titanium tetrachloride. Or I guess it would be titanium 4 chloride, depending on how you want to say it. Okay, so it all relates to the boiling point. We talked a little bit about this already, but the boiling point is a special time when the vapor pressure reaches the external pressure. Okay, so this is a phenomenon that happens that we call boiling, and it happens when the temperature reaches the point where the vapor pressure is equal to the external pressure. That is the definition of boiling point. So if you have a pressure cooker, you're increasing the temperature, you're increasing the pressure, inside the pressure cooker. That means the water that's inside can get to a higher temperature than 100 degrees before it boils, because it takes more and more temperature to overcome the intermolecular forces of the water when they're being pushed down by all the extra pressure inside the pressure cooker. So when the vapor pressure reaches the external pressure is when you've reached the boiling point for any substance. And I mentioned before we call the normal boiling point normal when we're at normal pressures, which is about 1 atm. So the normal boiling point, if the phrase normal is used, it means the external pressure is 1 atm. Notice here is the external pressure is different at different elevations. That means our boiling points here are all different values for water. If you're at sea level, it's 100. That's the way we normally think of it and experience it. But if you take it up On to Mount Everest, it goes down to 78 degrees Celsius because that's the temperature at which the vapor pressure equals the external pressure, and the external pressure has lowered itself quite a bit compared to at sea level. Hopefully that makes sense. So which of the following would have the highest normal boiling point? And here we're going to want to draw the line at 760 so that we can compare. When the vapor pressure reaches 760, which one requires the highest temperature to get its vapor pressure to reach 760? So as you can see, titanium tetrachloride here requires the highest temperature for the vapor pressure to reach 760. So therefore it has the highest normal boiling point. Okay, we're going to stop here for now, and this brings us to a very interesting point where we're going to start calculating heating curves. And we've made it through page 503, and now we're going to start back somewhere, page 504, 505, talking about heating curves. Stay tuned.